Hi, in this video, I'll be going through an application of learning differentiation for multivariable calculus. And likewise, like we had in one variable where we learned how to use differentiation to find the maximum and minimum of a problem set, in higher dimensions, two or more variables, there is an analogous statement and we are able to find the extreme values. And really this is a result from the extreme value theorem, which in generality you can watch my analysis videos for it. But now let's look at the case of two variables and practice on the questions type to get familiarized ourselves with finding the extreme values in two variables. And then with that you'll be able to generalize it to any variables. And so let's first define what a local maximum is. A local maximum is in a neighborhood, so it's like your domain intersecting some disk around A, B. In this neighborhood, all the values around it is less than FAB. So let's say AB has a value here, then you take a disk around here that intersects with this, which is in the domain. Then this neighborhood, every point inside it will have a value less than f of AB. Then that's a local maximum. And a global maximum is it occurs for every point in the domain. And similarly, for local minimum, it just means FAB is smaller than fxy for all xy's in the neighborhood. Local maximum and local minimum are known as local extrema, and global ones are called global extremum. And what we can notice is that global maximums are obviously local maximums, but local maximums might not be global maximums. So let's move on, and now we will show how to find the local extreme value. And this really comes from the first derivative test for higher dimensions. And it says that if it has a local maximum and minimum and the partial derivatives exist, then these partial derivatives must equal to 0, which also implies that all directional derivative equals to 0. And the reason for that is, if your local maximum or minimum, then now you restrict yourself to the line parallel to the x-axis or the y-axis, then you are a one variable case. And in that case, then your one variable derivative, which is your partial derivative, will be equals to 0 from what we learned in calculus. And so from what you learn from calculus, it means that the partial derivatives will be 0. And what you get is actually, you realize that the maximum point or minimum point, the extrema points, will have a horizontal tangent plane. And when we think about it, so we know that the extrema values will have this partial derivatives to equals to 0. So we can make a definition for when a partial derivative equals to 0 and what happens when it does not exist at all. Then we call this point a critical point. And so if it's differentiable and it has a local extreme value, by the first derivative test, it means that AB is a critical point because the fxy and the fx and fy are both 0. But the converse may not be true, because fxy and if AB is a critical point, it might not be that f is a local extreme value, because it's possible that the partial derivatives does not exist at that point. And so now we take a look at an example to familiarize ourselves. So we have find the extreme value of this. What we need to do is we need to take the partial derivative and equate it to 0. The reason for this is because of the first derivative test. It means that you can now reduce the number of points you're looking at to only the ones that make this partial derivative 0. Because if the partial derivative is non-zero, then it definitely cannot be a local minimum or maximum anymore by the contrapositive of this statement. And so you really only need to look at the points where fx and fy are both 0, and that the only possibility is 0, 2. And now you just need to check that 0, 2 is indeed the local extreme value. And you can do this by some argument where you manipulate the expression, or we'll later see when we can use the second derivative test to help us. And so a saddle point is a critical value, a critical point, so it fulfills this, but in every neighborhood it is not a local extreme value. So what you can think about it is, it needs to be an interior point first of all for local extreme, because you can see that if the endpoints can be local extreme, but they're not really turning points or critical points as we like. So a saddle point is really just a critical point but it's not a local extreme value. Next, we move on to using the second derivative test, and in this case it really is using this property of this discriminant, or you can call it the Hessian of a function. And what it says that if f has a local maximum, so first of all you need your second partial derivative with respect to x. So fxx is less than 0, and your Hessian is larger than 0. And it's a local minimum if your Hessian is larger than 0, but your fxx is larger than 0 as well. And if it's a saddle point if the Hessian is less than 0 and is inconclusive equals to 0, in which case you will rely back on your first derivative test, like how you did it in one variable calculus. And so if you look at this example, it illustrates the point on how we use the Hessian and the second order partial derivative to help us find whether it's a local maximum or minimum. And it's quite a routine step, and once you get to this point, you see that the Hessian is larger than 0, but the second order partial derivative is less than 0, which tells us it has a local maximum. And of course, what we'd like to note is that the local and global extrema might not exist. For example, y equals to ex, and really that's because it might not be bounded or closed region, or the function is not continuous in general. But if we know that the function is continuous and is bounded and closed, then it will attain the local maximum minimum, the global maximum minimum within that interval. And that is the extreme value theorem that we have proven in analysis. So I won't prove it here again. You can watch my analysis video on the proof. But what we like to now use is this idea of the extreme value theorem to formulate a method and a way to find this global maximum and minimum. And so what we need to first find is the critical points in the interior. And the reason for that is the local maximum or minimum, the global maximum or minimum, must lie either in the interior or on the boundary. And if it lies in the interior, then we know that it is a critical point. So first you find all the critical points, and then you calculate the values. Then now you consider the boundary case separately, because you don't know how the critical points will be like there. So you consider the boundary separately, and along the boundary you find the maximum and minimum, and you compare the values between these two Whichever is bigger is the global maximum, and whichever is the smallest is the global minimum. We take a look at an example to illustrate our point. And really, you just need to practice a lot, and these steps become very routine in solving the question. So for example, let's find the absolute maximum and minimum of this function. So we first need to find the interior points that are critical, and we just differentiate partially and we equate them to 0, and we get 1/2, and the value is 7. And then along the boundary, we want to maximize. We just need to take, let's say, this boundary first. So x equals to 0, we get this result. So we take y equals to 0 first, let's say. Then we get 2 plus 2x minus x squared. And then we just check, when it's 0 is 2, when it's 9 is minus 61. And this function has its own critical values at 3. And along x equals to 0, this will be the function. And we can get the respective coordinates of the segment that's critical. And then we need to account for this line also. And we just check through. And we compute all the different values. And we see that the maximum lies at 7. Is 7, and it assumes at 1, 2. While the minimum is minus 61, and it assumes at 9, 0. So you can check through the step-by-step workings to make sure that you understand. I'll lastly move on to what is known as the Lagrange multiplier method for finding global extremas under a constraint. And really, the idea and steps is very similar to what you have already done, so it's not too hard to catch on. But right now, what you want to know is you have an entire domain here. But in reality, in real life, there are certain constraints that restrict our function to certain values only. And so we need to, these constraints will trace out some intersection with the domain, and let's say it's like this. So what we need to do now is we need to figure out a way to find the global extremas along this line. And so what you do is you draw the level curve of f. So these are all the values f can take and how the curve looks like at different values of f. Then you have your curve somewhere along this space. And we see that it increases over here, over here, over here. Then it starts decreasing. And so it actually only touches the level curve. And so if you were to draw a gradient, a tangent line, it will be both a tangent to this curve and the level curve. And hence, the gradient vector of this curve and the level set will be equal or equivalent in the sense that they are scalar multiples of one another. So with this observation, we see that the gradient vectors is a scalar multiplier of each other. And when you are able to solve for the constraint under this condition, then you'll be able to find the extreme values in the interior. So what we need to do is that if the point lies in the interior and the extreme value is subjected to the constraint, then it is a critical point of f subjected to the constraint. And so now we need to look at the interior, but we have this equation and this equation to fulfill. Then we evaluate the f at all these points and we find the extreme values along the boundary. Then we just compare step 2 and step 3 and we just pick out the maximum and minimum respectively. One thing to take note is this is very similar to when you did the local extreme value for a general interior domain. So then in step 1, you just need to take the partial derivatives and then you equate and try to solve for x and y. But now you have 2 equations, but in this case, the 2 equations is you need to be subjected to your constraint, and your gradient vectors must be scalar multiplers of each other. So with this, you'll be able to calculate and find, and we'll take a look at an example to illustrate it. So you want to find the maximum and minimum of fxy subjected to this ellipse. So this ellipse, you need to form the level set first, so you bring the 1 over. And what you must do is you need to take note of these 2 equations. So gxy equals to 0 is this. And the gradient equation is, you need to differentiate partially here. So it's yi plus xj over here. And when you differentiate this is lambda over 4xi plus lambda yj. And when you shift this around, you get lambda equals to y equals to lambda over 4x and x equals to lambda y. And also y must equals to lambda squared over 4y. And hence y equals to 0 or lambda equals to plus minus 2. And then we just consider the cases where y equals to 0. X will then be 0, but 0, 0 is not on the ellipse, so y cannot be 0. And then we see that if y is not equal to 0, then lambda is plus minus 2, so x is plus minus 2y. And substituting, we get that y equals to plus minus 1. And therefore, the extreme values will be plus minus 2, 1 or plus minus 2, minus 1. Which makes the extreme values of x and y 2 and minus 2 respectively. And so that's a very step-by-step way of finding the extreme values of a function in 2 variables. You can of course extend this to multiple variables, and the Lagrange multiplier will still work, this method. And so that's the end of this video. I hope you have enjoyed this video. Stay tuned for more, and please like, share and subscribe. I'll catch you in the next video. Bye.